So the fundamental theorem of calculus part 1 gives us the easiest calculus questions that you can do. They occur on page 290 of your orange textbook. And no, they don't occur on page 290 at all. They occur on page 302. Page 302 of your textbook, which is here. So the important thing not to miss on this section is that you're not being asked to do these integrals. You do not do these integrals. You will not do how are you going to do that integral? We're going to learn later how to do that integral. But you cannot do that integral now. In fact, this one might be undoable. Yeah, it might not be doable. Several of these might not be doable. You're not doing the integral. You're finding the derivative of the integral. It says find dy dx on all these. All right, so here, by the way, is the way they would phrase this more aptly on the AP exam. So we're going to look at page 302, number 8. And so that problem, all it says here is y equals this integral negative pi to x of this thing. But then it says find the derivative of that. So here's how they would phrase that. They would say, what is d dx of this weird integral, which is the integral from negative pi to x of 2 minus sine t over 3 plus cosine t dt. All right, how am I going to find that derivative of the integral? Well, I'm going to do this. The negative pi, I'm going to forget about it. Does not matter. I'm just going to plug the x in for all the t's and say that equals 2 minus sine x over 3 plus cosine x. Done. End of story. All I did was replace the t with the x. That's it. Okay, now, it would be great if it would just stay that easy forever, but of course it's not going to because it's calculus. So next thing up is number 10. So number 10 says it's integral from 6 to x squared of cotangent of 3t dt. We want the derivative of that. So I'm going to always write that derivative because it makes it clearer what we're actually doing here. We're finding a derivative. We're not doing the integrals. All right? So once again, the 6 does not matter. I'm getting tired of writing this, but I guess I can keep writing it. Doesn't bother me. All right, now, so here's the trick. You don't just have x here, you have a function of x. So you're still going to plug the x squared in for that 3t, and you're going to say this derivative of this integral equal, because basically the derivative and the integral cancel out. That's all that's going on here. The derivative, the integral, they cancel out. And then the variables sort of shift around a little bit. All right, so the derivative of the integral cancel out. The x squared goes where the t is, so we have cotangent of 3x squared. All right, but here's the tricky part. This is actually an inside function, and we're doing a derivative. So I have to multiply times the derivative of that. So I have to go times, I'll say the derivative with respect to x of x squared, or we could call it g prime, which is what I usually call the derivative of the inside function. Not the derivative of this inside function, the derivative of this inside function. So that's times 2x. All right, and then it would be nice to write this as 2x cotangent 3x squared, and that's that. That's it for that one. All right, so now, the key is if there's a function up here, chain rule, put the derivative of the function out there. Put the function in, and then the derivative of the function out. All right, we're next going to look at number 14. Number 14, oh, they throw us another curveball. They're trying as hard as they can to make this difficult, but they can't because it's not. All right, so this time we have the integral from x to 7 of the square root of, oh my God, it's so complicated looking. But all we're going to do is copy it, plus t plus 1 dt. Notice again, this variable matches this variable matches this variable. These two do not. These two do not match. All right, but what's different? This time the x is on the bottom. Can I just ignore the x down there? No. To use the theorem, it has to be a constant on the bottom. So this must be a constant. All right, but it's not. So what are we going to do? What we do is we can do this with integrals. We've done this once in a while, but usually I don't use this theorem very much. But what you're going to do is you're going to say, I can reverse the integral if I put a negative sign out front. And we could talk about why, but there's a lot of rabbit holes you could go down. I don't think I will. It's essentially like, did you integrate this way or did you integrate this way? And they're opposite signs. Okay, is one way to look at it. There are other ways to look at it. But there's maybe a general theorem that's sort of worth noticing, is that the integral from b to a of f of x dx is equal to the negative of the integral from a to b. I should say the opposite of the integral from a to b of f of x dx. Okay, integral from b to a is the opposite of integral from a to b. You can switch the, basically you're like making delta x negative if you do this, if the b is less than the a. Anyway, negative. So I need to get the constant at the bottom by pulling out a negative. And then, you don't necessarily have to write this step. I'm just writing it to show where things are coming from. So it's the derivative of this negative integral, and then I can pull the negative out. Right? So then now I have the theorem exactly as intended. But you could just jump from here to here and say this equals negative. Now I've got the constant at the bottom, and now that constant doesn't matter. So now I've got negative square root of, just plug that x in there. It's no function, so there's no chain rule. It's just 2x to the fourth plus x plus 1. Done. That's it. So yeah, I'm inviting you, I wrote out a lot of things to sort of justify. You do not have to do that. I would jump straight from here to here and essentially jump right to the answer.